All right, guys, I think I'm going to go ahead and get started. It's 10 o'clock, despite what the clock on the wall over there says. I hope that you're doing okay today so far. I'm a little sluggish, I think, because of the weather, but just give me a little linear algebra to talk about, and I'll snap right out of it. It's usually works like a charm for me. So anyway, I hope you're doing well. I have a couple of announcements, and then we'll pick back up with this conversation about determinants that we were starting on Tuesday. First of all, there is homework due tonight. It's homework number 7. I see a couple prompts have been put on the board over here. And it's Thursday, which means I have a lot of office hours. I'll be around later on this afternoon and also tonight after my last class, after 5:30. Basically, I'll go back downstairs again and I'll be there until 10 o'clock with about an hour and a half break around 7. So it's all, if you ever forget what my office hours are, just check it out in the syllabus, and you can come in Zoom or in person if you want to talk about anything related to that. So yes, so anyway, that is the first thing, the homework that's due today. Your next homework after this one will be the last one before our exam. So homework number 8. And I decided to just go ahead and push this to be due on Tuesday. So you'll have a few days to work on it. It shouldn't be too bad. It's just some mostly computational stuff on determinants. So I hope that that'll go pretty smoothly. But something else will be happening in the meantime, which is that since we do have the midterm coming up, let me just remind you here. Midterm 1 is next Thursday. I remember I moved it. It was originally going to be on Tuesday, but I've moved it to Thursday, which I think is going to make things much nicer. And I've also talked about how for each midterm, I'm going to have some extra credit. For all of you who've stopped by to introduce yourself, which is, I think, just about everybody. If you still haven't done that, I might be generous enough to let you still come in this week and chat with me about just 5 minutes, your introduction. As long as you've done that, then you can do this extra credit. And the extra credit for this midterm is going to be coming in 2 parts. The first part is going to be a quiz that is optional. And I'm going to be sending that out well before Tuesday. I might even send it out today or tomorrow. And I will give you probably no more than 48 hours to work on it. And you will have to submit that back into Canvas. So you really need to be checking your emails. So there'll be an extra credit quiz. I have not got it quite ready yet, so that's why I'm not quite sure when I'm going to send it to you. So I'm just going to tell you that you should definitely be checking your email for that. These extra credit points will be added to your midterm score. We don't know what your midterm score is going to be yet, but whatever your midterm score is, I'll be adding points to it based on this quiz. And I'm talking like 3 or 4 points for this quiz. But there's another bit of extra credit out of 100, right? The test will be out of 100 points. So you can get a handful of extra credit points from this quiz. Just as a heads up, there will be something else coming up, which is going to be also for extra credit, probably another 3 to 4 points, is going to be some video notes. Now, that is not going to happen until after the midterm. So the midterm is on Thursday, the 26th. I'm going to be pretty much sending you a video to watch and take notes on right after that exam. So I don't want to clutter your inbox with this part yet. But that will also be coming, and that will actually be more or less required. I'm going to more or less expect everybody to watch this video. Not this weekend, but next weekend. And it will be a fairly lengthy video. It's something like 80 minutes or so. But I'll be giving you another 3 or 4 points of extra credit for doing that. So altogether, you can get a pretty decent handful of extra points added to your midterm through these 2 things. But only if you're checking your email, staying on top of the opportunities that are coming your way. Because obviously we only meet twice a week, and I'm not always able to get messages to you as quickly as I can through email. All right, so any questions about that? Yes.
For the midterm, do we need a calculator or no?
No, no calculators on the midterm. I am not a calculator person. You can leave things unsimplified. No need to worry about any of that. Just remember on this midterm, it covers chapter 1 through 3. I showed you my Canvas resources on Tuesday, so I won't spend much time on this. It's basically going to be homeworks 1 through 8. If you're thinking about it in terms of which homework assignments it is, we're currently working on number 7 for tonight. So one more assignment for next Tuesday, and that'll wrap up the homework for this section. And then also, we haven't done much group work yet. I've been putting it off. Oops, that's not right. I've been putting it off a little bit to make sure I get my lectures in. But I am hoping at least on Tuesday we'll do a couple more group works. So we did a couple of them in the videos that you just watched before I even got back into town. We did one last week, I think. I was hoping to get a couple more of them done before the midterm. Anyway, this is more or less what it's all going to cover. So that's the story on the midterm. So we have homework on Tuesday next week, and then on Thursday we have our exam. I'll send out a weekend, information preview email like I always do, and I'll probably have a lot of that stuff explained in that email too. Questions? Pretty good so far? Okay, and I will try to save a little time to look at these problems from tonight's homework in just a little bit. But I want to, my goal is to finish all of the material for the midterm today, so that we're a week ahead and you have lots of time. You don't have to learn a lot of new stuff next week. Next week, hopefully we'll be just getting ready for the test. But we'll see how it goes. Sometimes I talk slow, but we'll find out. Let me just remind you of the highlights from Tuesday's class, and then we will get back into it right away today. So the whole thing about determinants, which is just this number that we associate with a matrix, is that it has a lot of significance, in particular as a test for invertibility. So I can take a square matrix, again, it's only for a square matrix, but I can test whether a square matrix is invertible just by calculating the determinant, which is just this number. And if that number is not 0, then my matrix is invertible. In which case, then if I want, I can try to find the inverse of that matrix if I care about that. You'll remember that for smaller matrices, right, for 2x2 matrices or 3x3 matrices, we have a nice formula for this determinant. Like you can just kind of plug numbers into an expression. It's no big deal. But when the matrices get larger than 3x3, so as for example, the warm-up we're going to do in a minute is 4x4. If we have a larger matrix, right, then we cannot do the determinant directly from a simple formula. Instead, there's this process that I described on Tuesday involving these so-called cofactors, right? So for every row and column, like I and j value, there's a cofactor, okay? So like this matrix here would have 16 different cofactors, right? There's 16 different entries here indexed by 4 rows and 4 columns. So the I value here is just the row number, and the j value is the column number. And in this matrix, it would be ranging from 1 to 4, right? And the formula is that the cofactors are just plus or minus of the corresponding minors, right? And again, the minors are also indexed by the rows and columns, and there would be 16 of those for this matrix as well, right? And so you just take these minors, and then you sometimes do a sign change to get the cofactor from the minor. When do I do the sign change? Well, it's this -1 to a power. If that power is odd, right? I plus j is odd, then I have a sign change. And I don't generally remember this formula so much. I just kind of draw this little picture. I did this on Tuesday as well, where you just alternate plus and minus signs, and whatever the matrix is, this could stretch forever towards the right or towards the bottom, depending on how big the matrix really is. Okay, so that's how I would remember the rules for doing the sign changes on the minors. I just kind of draw that little visual. At least for me, it's the most helpful way. All right, guys, stop me if you have any questions as we go on. I'm just reviewing a little bit before we try an example again. But the big theorem was this cofactor expansion theorem that we talked about towards the end of class last time, which says that you can find the determinant of your matrix if you know how to find cofactors. So if you're able to do the minors and the cofactors, then you can find the determinant of your matrix. And in fact, you can choose any row or column of your matrix to focus on, right? So you get to pick. If everybody in this room chose a different row and a different column, we should all get the same answer, because it doesn't actually matter which row or column that you pick in terms of getting the right value here. And what you do when you do this expansion, as you can see from the formula, I know it's a little technical, it looks a little messy here, but all you're doing is you're going along either the ith row or the jth column and multiplying the entries from the original matrix by the corresponding cofactor that is indexed by that same position in the matrix, that same entry in the matrix. So, I can go along any row or column, which basically means you're going to need all of the cofactors from one of the rows or from one of the columns, depending on which row or column you chose to work with. Okay, so that was the idea. Is this all good with folks, or are there any questions on that? Just wanted to remind you of some of these highlights. Remember, the minors are obtained by crossing off the ith row and jth column and taking the determinant of the submatrix that you get when you delete that row and that column. So it's a smaller matrix. Hopefully it's easier to find that minor. Make some sense? Okay, let's try this example. We did one example on Tuesday, but let's just practice one more time on this just to get everybody warmed up today. So I have a matrix A, it's 4 by 4. So I don't have a nice formula that I can just plug straight into. Rather, I'm going to have to try to use this cofactor approach. So looking at this matrix, would anybody like to suggest what row or column might be nice to calculate this determinant from? Yes, what was your name again?
Angela,
Angela.
column 2.
Column 2, and why do you say that? Guys, that's beautiful. Yeah, if I see zeros in a row or a column, then those terms of my expansion are going to get zeroed out, and I don't have to calculate those cofactors. That's exactly right. So I'm going to do that. I'm going to do the determinant of A by expanding, and I'm going to put this in the notes so that we know what we're doing. I'm going to expand column 2. It's not that any other row or column is wrong to do, like any row or column is fine. But the best choice in terms of reducing your workload would be to use column 2. So if I'm doing column 2, that means that J is 2. So I come over here and I can write down what it would look like. A12, C12, plus A22, C22, plus A23, C23, plus A24, C24. No, I did that wrong. Sorry. These last two terms, I got it wrong. The J value is the second entry. Should be A32, C32, and then A42, C42. You don't actually have to write that down every time if you don't want to. You can just start plugging stuff in. But that's the second equation with the J value of 2. Look okay? And as was just pointed out, the 1, 2 entry, that's this entry right here, row 1, column 2, that's 0, right? And so is the 4, 2 entry, right? The 4, 2 entry is also 0. So the first and last term, we don't even have to worry about those, okay? And then all I have to focus on then is the second and third entries. Notice that A22 is 1. So I'm going to write this as C22, and A32 is 2. So I'll go ahead and put those numbers in that step. So it's just C22 plus 2 times C32. And the other thing I like to do kind of before I get into calculating these submatrix determinants is I like to get my sign changes figured out. So like the 2, 2 entry, and the 3-2 entry are these two entries. And I can see that on the 3-2 entry, right, the 3-2 cofactor, I do have to make a sign change. So I'm gonna convert these to minors. The first minor doesn't have a sign change, but the second one does. Right, so it should look something like that. So I've changed the sign on the 3-2 minor in order to get the cofactor. Okay, so we're just about there. And so now let's write down what these minors are. So the 2-2 minor, M22, right? And then it'll be minus 2 times M32. So I'll just go ahead and give myself space to fill in these matrices now. So the 2-2 minor, guys, I'm going to cross off row 2 and column 2. So I kind of cross these up. I would recommend that you do this kind of lightly, because we're going to come back in a minute and like uncross off a row and cross off a different row or column or whatever. And it's just, you start drawing heavy dark lines through your matrix, you'll quickly not be able to see what the numbers were in the first place. So if we cross off those, the second row and the second column, then the remaining 3x3 submatrix that's not crossed off is what we want to write down right here. Okay, so I just put in the numbers that are still left over after I cross off row 2 and column 2. Okay, and then we have another determinant to put down right here, which is the 3-2 minor. So now I need to be uncrossing off this second row and go down to the third row. So I cross off row 3 and column 2, and I write down the numbers now, and I have 2, 8, 1, -1, 3, 5, and 3, 1, and -4. So in this case, only the middle row of the matrix ends up getting changed by all of that. Once I have the 3x3 matrix, we could just use that arrow method that I explained on Tuesday, right? So we would recopy the first 2 columns just to the right of the matrix and draw my different arrows and do the calculations. I think I'm going to skip that part because it's just so computational, and I'll just have you check what these answers are. This first determinant should be -22, and then we have -2 times the second determinant turns out to be 44. So I will have you check that. Those are just 3x3 determinants. It's really straightforward to calculate those. And so that comes out to be -110. And that would be the final answer. I'll let you check the 3x3s, but other than that, that's pretty full details. What do you think? Any questions on this? Does it make sense? Yeah, go ahead, Jason.
Couldn't you also, instead of doing the
The arrow method?
arrow method, couldn't you also just repeat the process again and then take the minor?
You can do the cofactor expansion method even on a 3x3. And in fact, later in this semester, we're going to want to do that as opposed to the arrow method in some situations. So it's absolutely legitimate to still continue the cofactor expansion method within each of these. Personally, the arrow method to me is easy. So with the 3x3, I like to do it. But your point is well taken, because you can only use the arrow method if you have a 3x3 matrix. In fact, let me, you kind of segued right nicely for me right into doing another example where we're going to kind of see where we can't really use the arrow method very, very easily. So let me do this. Are there any other questions though, before I go on the one that I just talked about here? Everybody okay? All right, let's try this one. Let's find the determinant of A where capital A is this matrix. So give yourself enough room to write this one down. This is going to be larger. First row is 3, 6, 8, 1, and 7. The second row is 0, -2, 8, 6, and 3. The third row will be 0, 0, 5, 7, 9. And then the fourth row is going to be 0 and 0 and 0, 3 and -4. And the last row is 0, 0, 0, 0 and 1. Okay. So this matrix is 5 by 5 now. So when I do my cofactor expansion, I pick a row or a column, the minors, right, the submatrices that we get will each be 4 by 4. And then for each of those 4 by 4s, for each of them, I would have to do a problem that's about this big, right? And so there would be 5 of those in theory. You know, so it could be a lot of work because the 5 by 5s only reduce down to 4 by 4 minors. For each 4 by 4 minor, we have to do a whole nother cofactor expansion, which involves reducing down to 3 by 3 matrices. You can see that as the matrices get really large, this could become very tedious, right? There is something about this matrix, though, that's kind of friendly, kind of nice to us. Does anybody notice what it is? Nathan?
The upper symmetric, or triangular.
It's upper triangular, that's right, which actually makes it favorable if as long as I choose a good row or column to expand along. There's a lot of zeros in this matrix, so that actually can really work to our advantage. So for example, can somebody suggest a row or a column that would be really nice to expand along here? Yeah.
Row 5.
Row 5, yeah, I could go row 5 or also column 1. Either one of those would be good, the first column or the 5th row. If I do row 5, then, you know, when I'm thinking about expanding row 5, I'm going to have 0, 0, 0, and 0 for most of the entries. The only term that survives is the A55, C55. And A55 is just 1. And C55, first of all, guys, take note, 5 plus 5 is even, which means there's no sign change on that. In fact, if you look on this diagonal, these diagonal positions in any matrix will always have the pluses on them, which means you'll never have to change the sign of the cofactors. So this is just C55 is just M55. I cross off that row and column, and I do the determinant of, so I'll just call this M55. I just have to do the determinant of this 4 by 4. Oh, so I only had to do one 4 by 4. Okay. If I had expanded the first row, I would have had to do 5 4 by 4 minors. That would have been tedious for sure. But by choosing row 5, 4 out of the 5 terms are 0, right? Because remember, guys, these AIJs are, if they are equal to 0, the corresponding cofactors can be ignored. That's the beauty of the formula. So now I just have to do the M55, just one 4 by 4 matrix. And how are you going to expand the 4 by 4 submatrix there? Pardon?
Column 1.
Column 1. Okay, I could go with column 1, or I could go with the bottom row again. Notice that again, you know, there's a nice way to break this down. Like I think I'm going to go with row 4 if I could. It doesn't really matter. I'm going to expand row 4. So this one, I'm now going to use row 4. So I already have a 1 there. And when I expand row 4, I will again have 0, 0, 0, and then plus 3 times C44. And again, there's no sign change on the C44, so it's just whatever M44 is. And if I do M44, that means I'm going to cross off row 4 and column 4, and that leaves me now, I know this is getting a little hard to read it, but we have a 3 by 3 submatrix here in blue that I circled in blue. That's a 3 by 3 submatrix. And again, I can, well, now I can use the arrow method if I wanted to, or I could continue the cofactor expansion and I could say, well, let's expand the bottom row again. Right, if we expand the bottom row again, come up here, we have 1 times 3 times, when I expand along this bottom row again, we would get 5 times C33. And all the other terms would be 0. And I think you see what's going to happen with this. So again, this becomes 1 times 3 times 5 times M33. That's because again, there's no sign change in the 3 position. To do M33, I just have to take the determinant of this by crossing off row 3 and column 3, and that leaves me with this 2 by 2 right here. So, so we get 1 times 3 times 5, and I can do the 2 by 2 by expanding the bottom row if I want. Or I can use AD minus BC, which is actually going to give me -2 and times 3. And if you work that out, that comes out to -90. So that's just the final result there. So does anybody see how we could have sort of gotten the -90 from the very beginning, where these numbers are coming from? Yes, like?
Multiply all the diagonals.
Exactly. These are just the products of the entries on the diagonal. And so this is now a very nice observation that will work actually for any triangular matrix, right? I'm going to state that here for you guys. This is a really helpful theorem, which is that if A of n by n size is upper, or as it turns out, it's also going to work if your matrix is lower, triangular. So if A is an upper or lower triangular matrix, right? Then good news is we have a simple formula for the determinant. And that formula would be A11 times A22 times A33 and ... all the way up to ANN. This is a really helpful theorem. This is a really nice result. So, yeah, sometimes I might give you a larger matrix to work with, but if it's triangular, then the determinant is easy to get. I was feeling a little guilty the other day after class on Tuesday, because I think I told you that on the homework for tonight, that every matrix was 2 by 2 or 3 by 3. And then I looked at the assignment after classes. Whoops, there's a 4 by 4 matrix on the assignment. But you might have noticed the 4 by 4 was triangular, right? If the matrix is triangular, it's really easy to get the determinant by just multiplying the diagonal numbers. Okay, so that's a nice formula. Now, if my 5 by 5 matrix was not triangular, let's suppose that I had a 5 by 5 matrix that had absolutely no zeros in it at all, right? Just a horrendous set of numbers in this 5 by 5 matrix. Then, of course, it's not triangular, so I can't use this nice simple formula. So then I'm kind of stuck back with this cofactor expansion thing again, right? Or am I? Would there be, does anybody have any, does this example inspire any thoughts of maybe what we could think about doing, Eduardo? Oh, what if the matrix is not triangular now, but we could maybe do these so-called elementary row operations and bring it into a row echelon or a triangular form, right? That's a neat idea. Of course, you know, because you're going to be introducing zeros into the matrix. So maybe you have a matrix that has no zeros in it, right? We've been lucky so far this morning, everything's got zeros in it. But if your matrix has no zeros in it, what I might want to try to think about is, could I put zeros into that matrix by doing EROs? Exactly. So that is a question. I think I'm going to phrase it as a question. So it turns out, of course, you can do EROs to the matrix, but the question is, how do they affect the determinant? It turns out that as you do EROs to your matrix, you will change the determinant as you go along. That's kind of bad news, but the good news side of that coin is that actually it will change the determinant in ways that you can keep track of. And you can do bookkeeping with your EROs and keep track of those changes. So the question here then would be, given any matrix capital A of n by n size, can we do EROs to convert it to a triangular form. So that would be one question, but of course, the answer to that question is yes, because of course we can do EROs. So the answer to this question, can we do EROs and convert it to triangular form? The answer is yes, but we must keep track of how those EROs change the determinant. Okay. This is the point. This is what we're going to talk about. Okay, I'm going to come back over here. So actually, this is a good time to start talking about the properties of determinants, because that's actually going to be one of the first things we want to say is that the EROs do change the determinants, but we can keep track of this. So properties of determinants. This is a good time to just talk about this a little bit. Okay. So I'm going to talk about these EROs, but I'm also going to talk about other properties as well. So here's the first property, guys. If I start with A and I permute two rows, so let's say I do the PIJ operation. This is my usual little twiddle notation for that. If I permute two rows of the matrix A, then the new matrix, which I'm calling B, is going to have a determinant which is going to be a sign change on the determinant of A. So you guys are going to need to know these properties, right? The determinant of B is the negative of the determinant of A. So there's a sign change if you switch two rows, okay? The second ERO was if I start with A and I multiply the ith row by some scalar K in order to get the matrix B, then what happens over here is that the determinant of B picks up that factor of K as a multiple. So you get the determinant of B is just equal to K times the determinant of A. It's actually pretty easy to prove these things just by using the cofactor expansion formulas, okay? I mean, think about it. If I take the matrix A and I multiply the second row through by a constant, for example, then the entries of the second row, instead of A12, A22, A32, and A42, will be KA12, KA22, KA32, and KA42. The whole determinant would pick up a factor of K. Totally reasonable, just even from the cofactor expansion formula, okay? And then finally, the third ERO is where we take the matrix A and we add the K times the ith row to the jth row to get the matrix B. And if we do that, it turns out, and again, this takes a moment to sort of explore, but I'm going to just tell you the formula here. The new matrix will actually have a determinant that does not change in that case, which is super nice. Super nice that if you add a multiple of one row to another, the determinant does not change at all. So it's totally unchanged by that. So these first three properties are just, these are how EROs affect the determinant of A. Okay. So it's good to kind of have those in our list. I would like to sort of show you how this can be helpful to solving the determinant of a matrix. But before I do that, I'm going to add, would like to add one more property here right now that is related to the ones we just talked about. What if I So this is not an ERO, but what if I wanted to know the determinant of, let's say, K times capital A? So here I'm taking the matrix A and I'm multiplying the entire matrix by K. Would that be somehow relevant or related to any of the first three properties there?
Related to the second one.
The second property, yeah. And does anybody have an idea what this formula is going to be over here? Alex?
It's gonna be a to the power of n.
Beautiful. K to the power of n times the determinant of A. That is correct. A lot of people don't put that nth power there, but see, what you have to realize is that when you take K times the entire matrix, you have actually scalar multiplied every row of your matrix by K. And even if I do one row multiplied by K, the determinant picks up that factor of K. So that happens for every single row of your matrix. So just as an example of this one people kind of sometimes get a little mixed up by. So if A is 4 by 4 with the determinant of A, let's just say it's equal to 5, then I could ask you to compute the determinant of 2A. Like, what would be the determinant if I literally double the matrix? If I just double every single entry in the matrix, what would be the determinant? And a lot of people would just look at this and say, oh, it's just 2 times 5. And they give me an answer of 10, which is the natural thing to say, but it's actually not correct. Okay, so for the solution here, we'll just solve it right here, just very, very briefly. For the solution, we are going to use property 4. So use property 4, which we just wrote down a moment ago. And so the determinant of 2A would actually be 2 to the power of 4 times 5. And so 2 to the 4th, I think, is 16. 16 times 5 is actually 80. So this becomes the right answer then. Okay, so just be a little careful with that one. If I multiply the entire matrix through by a constant, you actually have to power up that constant to whatever the size of the matrix is. In this case, the 4. So why is it the 4th power? That's coming from the 4 by 4 size here. Okay. Questions on that? Yeah, go ahead.
But for number 2, that's not under the same rules, right? So you can just multiply by K. You don't have to do the power.
Right, because here I'm only multiplying the ith row only. So I'm just doing one ERO to it. This is almost like I did n EROs. I multiplied the first row by K. I multiplied the second row by K. I multiplied the third row by K. And every time I did that, I've actually applied property 2 n times, right? And that's why these K's pile up and you end up with a K to the n power there. Yeah, that's a good point. Okay, but actually, so this is not where, this last example is not where the real power of this whiteboard is, right? The real power is that we can do EROs. This was Eduardo's idea. We could take a matrix that's not triangular yet and try to do EROs on it to bring it into a triangular form so I can use my theorem here, right? So I'd like to show you an example of that, sort of the full-blown power of this. So let's do another example. By the way, I'm not done with my list of properties. So we're kind of inserting some examples into this list right now, but I am going to add to that list a little bit more in just a few minutes. But here's what I'd like to do. I would like to use EROs to find the determinant of A where A is equal to, here's the matrix. I'm only going to do a 3 by 3 for this example, guys. So I'm going to take the matrix 2, 1, 3, -1, 2, 6, and 4, 1, and 12. Now, of course, as you can see, guys, I don't need to do EROs for this determinant. It's only 3 by 3. So I could use the arrow method. Even if I had to do cofactor expansion, it wouldn't be the end of the world, right? It would actually be pretty easy. So I'm using a pretty small matrix here that I really normally wouldn't use this strategy with. But that's just because I want to pick something that isn't going to take me 30 minutes to solve it. This will be pretty fast, okay? So let's pretend we don't want to use the arrow method, and we also don't like the fact that there's no zeros in this matrix. What I'm going to do is try to do EROs on this matrix, convert it into row echelon form, which is triangular in nature for a square matrix, and then use the theorem over there. Okay, so here's how I would approach this. For the solution, I would start with my matrix A. Can somebody give me an ERO that would be maybe a good place to start? P1, 2. I want to get a 1 into the upper left corner of the matrix, and a -1 is pretty good. So let's permute rows 1 and 2. So I'll do P1, 2, and then the first row becomes -1, 2, 6. The second row is 2, 1, 3, and the third row is 4, 1, 12. It look like that. Okay. Anybody else want to suggest an ERO that we could do next at this point? Yeah, go ahead, Angela.
Multiple two to seven.
Beautiful. 2 times the first row. I'm going to add that to the second row. Let me go ahead and write that down. The first row stays the same. The second row, if I take 2 times the first row and add it to the second row, it'll become 0, 5, and 15. And is there another ERO that we could do at the same time? That would be pretty easy, Jerry.
You add the first row to the third row.
1A13 of
4.
4, right, exactly. 4 times the first row. Going to add that now to the third row. So take 4 times the first row, add it to the third row. We're going to get 0, 9, and 36. Okay, so we're doing some EROs here. Okay. By the way, you know, it really isn't necessary to get it into official row echelon form. I know some of you are thinking, well, wait a minute, -1, that's not a pivot. I need to turn it into a 1. Actually, you don't really need to do that. When I said convert it to a triangular form, that really is good enough, okay? Because the theorem doesn't say that A has to be in row echelon form. It just has to be in a triangular form. So it's okay to have a -1 in the upper left corner here. Okay, can somebody suggest a good ERO that I could do from here to get to the next step? Go ahead, Audrey.
We could simplify the.
Okay, how about we multiply the second row by 1/5? I kind of like that because I want to eventually get a 0 here, and it's 5 and 9 are not really jiving too nicely with that. So let's just get the second row cut down by a factor of 1/5. So this just becomes 0, 1, and 3, and I'll leave everything else the same. And now I can take, now I want to get this 9 to become a 0, and how can I do that? Yeah, go ahead.
Multiply the third row with 1, 9.
Now I could do that, but that would turn this into a 1. So I'm still not getting quite the triangular form. I think we could go straight to the triangular form. Somebody see how I could do that? Mark,
By row 3 by.
that's what he said. Yes, Mira.
Second row by -9.
I could multiply the second row by -9. There's a faster way, guys. What is it? There we go. That's what I wanted to hear. Take -9 times the second row and add it to the third row. That's the only way you're going to make a 0 here in one step. Okay. It's not necessary to turn the 9 into a 1 first, and then you'd have to do another step after that to turn it back into a 0. So let's just go straight to it here. Okay. So the first row stays the same. The second row stays the same. And if I take -9 times the second row and add it to the third row, I think 36 minus 27 is 9. That's what we would have. Okay? Does that look okay to everybody? What I kind of like about what's on this board here, you guys did a great job with that. Every type of ERO is showing up here so we can talk about what we would do. So guys, this matrix here, I know what its determinant is because it is triangular, right? Our theorem says, oh, if the matrix is triangular, just multiply the main diagonal entries, right? So what would be the determinant of this matrix right here? -9, right? So I just take -1 times 1 times 9. Now, what I'm going to do, I ultimately want to figure out what's the determinant of A. So I am going to trace backwards through the work that I just did, keeping track of what ERO I did and those properties over there, right? So if I got this matrix by doing the A operation, then if we look at the matrix right before it, can somebody tell me what that determinant would have been? Still -9, right? Because why? Because the A operation, what effect does it have on the determinant? No effect at all, right? If I add a multiple of one row to the other, there's no effect on the determinant. So whatever these two matrices have to have the same determinant because they are just one ERO apart, and that ERO is an ERO that has no effect on the determinant. Does that make some sense? Slow me down if not. I see a couple people don't look too happy yet. So I'm using these three things right here. And in particular, I'm using property 3, right? So this is property 3 says this determinant is the same as that determinant. Okay. Now we come to the tricky one. This is the tricky one, the M operation. Sarah?
Oh, I was just jumping ahead.
Oh, you're jumping ahead. Okay. Well, I'm going to be ready for you in just a second. Do you have an idea what this determinant would have been?
Would it be?
So that's the tricky part of this. You have to remember here that we are actually going backwards through our work right now, right? We're actually going in reverse. So if we went from here to here, we've multiplied by 1/5, and the determinant would be multiplied by 1/5. But we have to imagine that we are going from here, which is the determinant of -9, and trying to figure out this determinant to go this direction. When I go this direction through my work, does everybody see that I have actually, if I think of it this way, I've multiplied the second row by 5? Not 1/5. There is a reciprocal here that has to happen when you're going in reverse. So the -9 actually needs to be multiplied by 5. And so we would actually get -45. This is the one step that I think can be a little tricky for folks. If we were going left to right, we multiply by 1/5. But of course, now we're going from right to left. So we reverse that or we reciprocate that and it becomes a factor of 5. Okay, Eduardo.
If we were to have multiplied row 2 by 5, instead would we just be dividing by 5 for the
Right, so if I went this way by multiplying by 5, then when I go backwards, I would be dividing by 5. Yeah, absolutely true. Yeah, so when you're going in reverse through your EROs, it makes no difference on the first one because it's just a sign change, and the third one, no change at all. But on the second one, there's a reciprocal that comes into play here. Yeah, Blaine. So normally you're starting with normally this is the situation. You're starting with a matrix whose determinant you do not know. And you are converting it into a matrix whose determinant you do know, but this isn't the one that you wanted to know. So you are generally going to be thinking about going backwards through your work here. Yeah. So this tracing backwards thing is actually pretty common. Okay, can somebody tell me then what would be the determinant of this matrix if I keep going backwards here?
It's 45.
It's still, what'd you say?
It's 45.
45?
Positive 45.
So this one's -45. I've done the A operation. What effect does the A operation have on the determinant?
Oh. Sorry,
No
I was
effect at
I was
all.
Jumping ahead, that's why.
That's okay. This one is actually exactly the same as that one. Okay, it's exactly the same as that one. Okay, and then finally, what would then be the determinant of A at the very beginning here? Positive 45. Here I'm doing the permutation, right? P12. The P operation puts in a sign change. So this would be 45 and this would be the answer. This would be the answer. Does that make sense to everybody? You know, I also want to point out here, guys, that you don't have to go all in on this ERO approach. Right? Yeah, it was nice we went all the way to the triangular form, but let's say you have a matrix that has no zeros in it, and you decide you do an ERO, you do an ERO. Let's say you get to here, and you're like, oh, well now I'll just do cofactor expansion. And you could just do the cofactor expansion here, get negative 45, and then you would only have to trace back this far. So what I'm saying is you can mix and match these techniques. You can say, yeah, eventually I'll do cofactor expansion. I'm not going to bring the matrix all the way to a triangular form. I just want to get some zeros into the matrix so that it's a little bit easier for me. And you could say, yeah, I'm not gonna go beyond this point. And you could just play this game up to here. Stop here, say, it's not triangular, but I don't mind. It's got enough zeros in it that I can get the determinant pretty easily. And then you just have a smaller backwards tracing that you have to do from there. So feel free to kind of mix and match these techniques. Okay, let me say, actually, this would be a good time to do this other problem from the homework, because there's a problem in the homework that's very similar to this, which is number 35 on section 3.2. So I'm going to do one more example while we're kind of at this good stopping point. Section 3.2, number 35 from today's homework. What they did is they gave you this matrix A, which just has A, B, C, D, E, F, G, H, I in it. So they just said, suppose you had a 3x3 matrix like that, and then they just made up a number here. The determinant of this matrix, what did they say? They just said, suppose it equals -6. So consider this to be the given. This is the given information. The determinant of A is -6. And then what they ask you to do, they ask you to find the determinant of a new matrix, and the new matrix is D, E, F on the first row, and then the second row is -3A, -3B, -3C. And then the third row is G -4A, H -4B, and I -4C. No, sorry, that's not right. That is not what the question says. The bottom row, I got the numbers wrong here. G -4D, H -4E, and I -4F. That's better. Okay, so this is one of your homework problems for tonight. And it is possible to do this problem by doing the arrow method on this matrix here. You could do the arrow method. You'll get some big alphabet soup of A, B, C, D, E, F, G, H, I, J, H, I, right? And then you'd somehow try to extract the arrow method result from A, which they give you as -6, and try to like insert that into the calculation. It's an algebra mess. It is possible to do the problem that way, but I have a much better idea now based on what we've just been talking about, which is it looks to me like this matrix can be viewed as the original matrix with some EROs that have been done. Excuse me. So we can just look at this and say, I wonder if we could write down the EROs that have been done here. So for the solution, excuse me. For the solution, I can imagine starting with A. And like, can you just visualize like what would be one of the EROs that happened to take me from A to the matrix that I'm trying to figure out. Angela?
Muting the second row and the first row.
Right, the first two rows seem like they got permuted, right? D, E, F is now on top, A, B, C got moved to the bottom. So I could imagine that there was a P1, 2 here that was applied to A, and that would have brought me to, I guess I could write out the whole matrix. So the D, E, F would go on top, the A, B, C would go in the middle, and the G, H, I is still on the bottom. And from there, again, it's not quite the same as the matrix that we're looking for. Is there another ERO that you can sort of see it, that it must have happened here along the way? Nathan?
Multiply the second row by -3.
Okay, the second row now, exactly. This is, the second row has been multiplied by -3. So I can see that as well. So the first row would be D, E, F. The second row is now -3A, -3B, and -3C. And then the bottom row is still the same. Okay, so that looks good. And the first two rows are now matching up with the first two rows of the matrix that I'm being asked to find the determinant of. And is there another ERO that has happened? Johnson? Uh-huh. Right, so we took -4 times the first row and added it to the bottom row, and that actually takes us to the matrix. I'm sorry, this is called B in the question. They called this the matrix B, so I'll just write B for that. Okay? So, but there is one big difference between this example and the one that we were doing a moment ago over here. And the difference is that on this example, right, we started with a matrix whose determinant we did not know. And we proceeded to put it into triangular form, which is a determinant we did know. And so then we had to trace backwards through the steps. Over here, am I going to want to be analyzing this forwards, or am I going to want to be analyzing it backwards? This time forwards, because I actually know what this determinant is, right? They gave us that. So this determinant here, I'll just put it below here. The determinant here was -6. Right? And now I'm going left to right. Okay. So you don't have to memorize anything. You just have to remember which direction are you going through the steps, right? In this case, I'm going forwards. So when I permute the first and second row, I pick up a sign change. And then when I multiply row 2 by -3, I really am going from left to right. So I really do want to multiply by 3. So sorry, by -3. I'm not going to do a reciprocal on this one because I'm going forwards from left to right. And then finally, the A operation has no effect. So the answer to this problem should be that the determinant of B is -18. Right? So seeing these two problems side by side, you can see that, normally you'd be doing this kind of problem, where you would start with a matrix you don't know and proceed to something that you do know. That's normally how you would do it. Okay, let me write down a couple more properties of determinants, and then we're going to take a 10-minute break. But are there any questions on either of these two examples in the middle here? Audrey?
Same group. Start with everybody was commuted, so now we have to find.
Right, we know this determinant, but we don't know this determinant, so we're actually going from left to right through these steps. So whenever I write this ERO down, it's sort of going from here to here. It's always left to right. You're not writing it in reverse.
Okay.
But then on the earlier problem, we were tracing backwards through our work, so we had to take a reciprocal of that K value. That's all. Yes.
For this problem, I tried just finding the determinant of A and then the determinant of B.
Uh-huh.
And then it ended up kind of canceling.
Were you
out.
able to get it to work?
Yeah.
Okay, that was what I was saying earlier. You can do it that way.
Okay.
It's algebraically more work, obviously, but yeah, that's totally doable.
Okay.
Yeah. Okay, let me add a few more properties to this list and then we'll take a short break. So I'm gonna go back to my list of properties and I'm gonna continue my properties of determinants here. So these are gonna be sort of more, not so much about EROs, but just more general types of properties here, so. Smudged badly on me here. So the first one is, what if I took a matrix A and I transposed it? This would be a natural question. If I switch the rows and columns, so we're getting away from EROs and we're talking about other kinds of things that we could do. Turns out that the transpose has no effect on the determinant. So that's an easy one. The next one, number 5, would be, what if I did, say, the determinant of A times B? And so if I multiplied 2 matrices together and I want to know, well, what's the effect on the determinant? The answer is that you do exactly what you would like to think you would do, which is you just individually find the determinants and multiply them separately. So I can just do the individual determinants and do a multiplication there. These things, technically they require proofs. Technically you would use the cofactor expansion theorem to really understand it and explain it. It's very technically cumbersome and not very enlightening in my opinion. So that's why I'm kind of just writing these down for you. It's not anything that interesting. What about the determinant of the inverse of a matrix? So if I wanted to take the inverse of A and take the determinant of that, it turns out that the formula for that is 1 over the determinant of A. So we take a reciprocal in this case. Keep in mind that you don't want to be dividing by 0. If the determinant of A was 0, however, then there wouldn't be an A inverse, right? It wouldn't even make sense to look at the inverse of A because that's our test for invertibility. If the determinant is 0, it doesn't have an inverse. So that makes hopefully pretty good sense as well. Oh, sorry, that's pretty much it for my properties. I do want to add maybe one more thing. I'll just refer to this down here as a warning property. Mostly because it's not a property at all. And that is, there is one thing missing from this list that you might expect to be in the list. And then you find out it's not, which is, you might wonder, well, what about the determinant of A plus B? So you might wonder, if I added 2 matrices together, could I do something with this? And the answer is that there is no formula for this. In particular, you cannot just add up the separate determinants, okay? So this does not equal the determinant of A plus the determinant of B. That's tempting. It's very tempting to write that down, but that is not correct, in fact. Yeah.
That's actually one of the true false in the homework, so like what's the rationale we should give for that?
Yeah, so when something like this is false, what I would recommend is that we write down a specific example. Let's try it. Let's see if we can do it. It's in the homework, so this is false in the homework, and so the question then is, well, how would you justify this? Maybe, in fact, this might even be, is this the one that's 3.1 part E?
Yeah.
Yeah, so I'm doing one of your homework problems again. Turns out for any n by n matrix, the determinant of A plus B does not necessarily equal the determinant of A plus the determinant of B. So let's give an example of this. So an example here, and this will solve true false E from section 3.1, which is on the sideboard over there. So we'll just do this one right now. So what I need is an example. When something is false, right, we need an example. If I say all Thursdays are sunny, right, then what you have to do is wait until there's some Thursday that's not sunny, like today, and then say, here's my example. The statement was false. So let's try and make a couple of matrices that we want them to both be 2 by 2. And let's try to make them nice. of course, 2x2s are easy to do the determinative of, but can we come up with a nice matrix here? Do you have an idea? What's your favorite matrix?
201.
1201. I love it. 1201 is a great one. And Blake, what's your favorite matrix? Sure. 1001. All right, let's try it. Let's see how that works. So the determinative A, can somebody tell me what will be the determinative A right here? Example. 1. Just the it's triangular, so it's 1 times 1. And what about the determinative B? 1. All right, let's do A plus B. A plus B, I just add these together, slot by slot. I have 2, I have 2, I have 0, and I have 2. Is that right? Yeah, 2, 2, 0, 2. Okay, what's the determinant of this? It's triangular again, right? For a triangular, I love that you guys gave me triangular examples. So nice. And that's because I just have to multiply the diagonals. And so I get 4, and I can see that that does not equal this plus this. 4 does not equal 1 plus 1, and so you've got your example. Okay, almost anything you would try would have worked here, but that's certainly one good counterexample. You know, another thing we could have done is we could have put, so this is fine, just leave it the way it is. You don't need to change anything in your notes. I just wanted to point out, we could have done just the negative of A. Right, and then these numbers would still be the same, but now when you add them together, you would have gotten all zeros, and then you would have gotten 0. This would have been another example. What this actually shows is that you can start with 2 matrices that are both invertible. Determinant's not 0, but after you add them together, it's no longer invertible. So invertibility does not play nice with addition. Determinants do not play nice with addition, right? The plus operation is not so good, but multiplication is good. Transposes are good. Inverses are pretty predictable, right? These are all properties that we would maybe expect. So just wanted to get this all down. We know how the EROs affect the determinants, and now we know how transposes, products, and inverses affect determinants as well. So it's a pretty good deal. Let's take a little break, and when we come back, I'm going to talk about the adjoint of a matrix as well as Cramer's rule for how we can use determinants to solve other types of problems. But it's about 11:07, so I'll probably start up again at about 11:15. But go ahead and grab some fresh air and decompress for a few minutes.
I'll get back to frame, most, we still have to watch it.
Does it say that on there? Oh, I'll probably take that off. Yeah, that's right. Sometimes, some semesters I get to it, and some semesters I don't, and if I don't, then I have to make people watch it.
This one's.
Look at me. No. I was telling you. You know, it's like anybody, because I was like, who's probably this really? Then I got through school, and I was like, oh. That's just weird. So actually, I'm just like this. I have three jackets. I'm not ready for that.
Is it gonna rain?
Today.
Right from now.
No, it's just sunny.
What'd you say?
It's just sunny.
Tomorrow or today?
Oh,
It's gonna say it's gonna rain today and I'm just resting.
I know, why is it always wrong?
I was driving and then it was misty and I was like, oh, no clouds and I sort of like.
Oh, so it did it this morning?
Well, I was driving. I like
It's really right before I was outside, cause I just went outside, it was totally like not raining, but it was wet.
what's in my bed.
Yeah.
Yeah, it was just like till 8:30. Yeah, but I think I actually woke up at 9. And then I was like rushing around trying to get out. Yeah, that's right. So you just have to sit in your car for like.
Yeah.
Are all your classes every day early for parking?
Yeah, I have a lot of attending classes for 4 days.
Well, then that covers it.
Friday, so. There's no
No,
one here.
yeah.
I don't have to do it. Because isn't it?
So.
When they get them made, when they go back.
Yeah.
Like the other way, it's like, oh, again, like, you know, the goes nowhere, like, that lady goes down, like, it's back, right, in the morning. And makes it back. That's, you know. Weekend, yeah. Oh, just weekend. Like, that's how weekend when you want to use all those.
All right, guys, I think maybe I'll go ahead and get started here again. Just because, yeah, I still have a little bit more I want to try to cover today, and I should finish all the material today, which was great. It means on Tuesday, we're gonna have time to review and do some group work, answer homework questions, all that good stuff. Tuesday should be pretty chill. Anyway, I do want to do this problem right now from the homework. It was on the sideboard over there. I noticed that, and I think this is a good one to look at because it's a nice review of some things actually going back a little bit. So if you could just take a look with me here on this one. I have a linear system of equations here. And you'll notice in this linear system, there's a constant k. We kind of did an example like this on Tuesday as well, where there's a scalar that's actually some variable. We don't know what it is. And they're just asking you, for what values of k does this have infinitely many solutions? They could have done all three cases. They could have said, when does it have 0 solutions? When does it have 1 solution? And when does it have infinitely many solutions? I mean, we could have done the trifecta of possible outcomes here. Does anybody have an idea when this system would have no solutions? We did one just like this on Tuesday. It was on your homework. Johnson? It's never, right? Why is it never? it's homogeneous, right? It's a homogeneous linear system with all zeros on the right-hand side. And so that means you'll never get a pivot. See, if I were to write down this augmented matrix, this far right column, yeah, it's gonna have all zeros in it. So if there's all zeros in it, then that column will never have a pivot. So it doesn't matter what K is, this system, it will never be inconsistent. So your only two options really are these two. Those are your only two options. And do you guys remember anything about the case of having a unique solution? What would be true about the matrix in that case?
No free variable.
No free variables. Is there another way to say it? Anybody?
There we go.
Eduardo?
Would it be like the rank is the same as the number of pivots?
The rank is the number of pivots.
Of the n by n.
Right. So the rank would be 3. That is also correct. Can anybody give me another way to say it? Yes.
The last row is all zeros.
For one solution, I would say the last
Uh,
row should not be all zeros.
Never mind. I was mixing them up.
Yeah. I'm looking for another word. What about the coefficient matrix? I'm looking for one very important word. That is actually true. It's a little deeper than what I'm going for, though. I'm looking for something really surface level. Blake. There we go, which is another way of saying that the matrix is invertible. That's what I'm looking for, right? So this would be if A is invertible. And so, of course, that means that this case would be that A is not invertible. Guys, that was a great review. All of the things you were telling me were correct, and they were part of that list in that invertible matrix theorem. So really good to do that. So how am I going to decide whether this system has one solution or infinitely many solutions? I could do EROs here. That's what I did on Tuesday. I took this matrix, I row reduced it, and I analyzed where the pivots ended up. But we have a sort of a better idea now that this matrix, it's 3 by 3, may or may not be invertible. And if it's not invertible, that would just mean that the determinant is equal to 0. Invertible would be that the determinant is not equal to 0. That's our test for invertibility. So I'm going to suggest that all you need to do here, guys, is if you want to know when does it have infinitely many solutions, you just need to take the determinant and set it equal to 0. You can use the arrow method on this. It'll give you a quadratic equation involving k. And that can be solved pretty easily for k. Audrey.
Oh, I'm forgetting, so like, why does the amount of solutions, how does that relate to whether it's a good one?
Well, for a general system, for a general linear system of equations, we might not even have a square matrix. So I don't want to get myself too attached to linear systems and invertibility of the coefficient matrix, because most of the time my linear system doesn't even have a square coefficient matrix. I can't even talk about whether it's invertible or not. But if my coefficient matrix is a square matrix, right, then I have exactly enough pivots to go right down that main diagonal, which is what would happen if the matrix was invertible. And otherwise, it would be not invertible. So it's really just this connection here. I mean, also, you'll remember in the invertible matrix theorem, A is invertible, and then the very next statement, what was the very next statement? AX equals B has a unique solution. One solution, and in fact, we even know what it is. So again, we're just going back a little bit to some of the points in that invertible matrix theorem. So unique means one, right? One solution is tied up with A being invertible. Yeah, Blake?
Just to say that in another terms, all square matrices, are they all consistent? Or are there cases where they're inconsistent?
Oh, they could definitely be inconsistent. They could definitely be inconsistent. You could have this thing. x plus y equals 1, x plus y equals 2.
Does that have anything?
It's a square matrix, but it's not invertible.
Does the consistency or inconsistency of a matrix have anything to do with determinants at all?
So if the coefficient matrix is square, then we can talk about the determinant, and if the determinant is not 0, then there will be a unique solution. That means it is consistent. So invertible lines up with consistent, right? For sure in that case. Okay. So anyway, I'm gonna leave it to you guys. Do the, I'll let you check this out. Do the arrow method to find the determinant of A. You're gonna set that equal to 0 and solve for K. That's how that works. And there'll be 2 values of K. You should get 2 solutions for K because it's a quadratic equation, as you'll find out when you do the arrow method on that. Okay. Hopefully that's pretty good for the homework. If there's more questions on the homework, I'll just ask you to stop by my office hours today and I can help you. I think I've done most of the bigger issues from the assignment. What I want to do next though is Tuesday, I wrote down why are determinants important? Up with determinants, remember? This idea that, yeah, I really think they're cool. So they're a test for invertibility, but there's actually more to it than that. There's another thing I want to mention, and I put it in your notes on Tuesday that I was going to talk about it today. So let's make sure that I do this, which is I want to talk about the adjoint method for actually finding A inverse. So now I want to move into finding the inverse of a matrix, not by doing the Gauss-Jordan method with the EROs, but instead I'm going to find the inverse of A by using determinants only. Okay, so I just need a couple of quick definitions to get this going. Here's a definition. This is really pretty short. This is a pretty short little conversation. If every entry of my matrix A, which is again going to be n by n size, if every entry of this matrix is replaced, okay guys, we're going to replace every entry of A, and if it is replaced by the corresponding cofactor. So here's where the determinants is going to come in. The corresponding cofactor, if we do that, we get what is called the matrix of cofactors. So this is what I'm defining right now, matrix of cofactors, and I'm going to denote that M sub C. The matrix of cofactors. This is essentially a matrix that we obtained by just replacing everything from the original matrix by the corresponding cofactors. Let's look at an example of that. Let's say I take the matrix capital A to be, I'm going to use a 3 by 3 example here. So let's take A to be the matrix 2, -3, 0. Second row is going to be 2, 1, 5. And the third row is 0, -1, and 2. So we'll take a good 3 by 3 matrix here. And then what I would like to do with this example is I would like to find the matrix of cofactors. Again, this is just the lead up to how we actually can find the inverse of A. Part of finding the inverse of A is going to be to first find this matrix. So this is the part that's really the guts of this little section, is finding this matrix of cofactors. So the solution to that is, M sub C. So just so everybody's clear what this, what is this M sub C thing? It's called the matrix of cofactors, and I'm just going to put all of the cofactors, the C11, C12, C13, all of these cofactors are going to be placed into the slots of this 3 by 3 sized problem that we're working on. So I have to find all of these cofactors. So just make sure we understand how this works. So if I want to find the 1,1 cofactor. Right? So I come over here, I say, what's the 1,1 cofactor? Well, to find that, I cross off row 1 and column 1. That leaves me a 2 by 2 submatrix. What is the determinant of that 2 by 2 submatrix? AD minus BC, right? 2 minus -5, that would be 7. So I put 7 here. So I put 7 in that position of the 1,1 cofactor. Right? Let's try to do another one, because we have to do all 9 of these. Right? There's 9 cofactors here. What about the 1,2 cofactor? Here's the 1,2 position, row 1, column 2. So I cross off row 1, I cross off column 2, and hopefully you can see about 4 numbers there. What is the determinant of that little 2 by 2? It's 4, right? 2 times 2 minus 5 times 0. So do I write 4 here? Negative. Aha, remember the sign changes, right? The cofactors have sign changes in the odd positions. So just to remind you, we have plus, minus, plus, right? Minus, plus, minus, all this stuff. Those sign changes. So we do have to keep track of that when we're writing down these cofactors as well. Okay. Great. Let's do the 1,3 cofactor. I will cross off row 1 and column 3. What's the determinant of that little 2 by 2?
-2.
-2, right? 2 times -1 minus nothing. That would be -2. Do I need to do a sign change?
No.
In the 1,3 position, do I need to do a sign change? No, that's -2. So we leave it just the way we found it. We do not change the sign. Let's go to the 2,1 cofactor. So that's row 2, column 1. I cross off the first column and the top row. Sorry. Cross off the middle row and the first column. What's the determinant of that little 2 by 2?
6.
AD minus BC, -6. So what do I write over here? +6. I do a sign change, it becomes a +6. Okay? Great. What about the 2,2 cofactor? I'm gonna let you guys try it. What's the 2,2 cofactor going to be? Cross off the middle row and middle column, take the determinant of the 4 outside corner entries. That should be 4, right? Do I change the sign? No, I leave it as 4. All right, beautiful. How about the 2,3 cofactor? So I cross off the middle row and the right column. What's that cofactor going to be? So the determinant is -2, and so what's the cofactor over here? +2. You have a sign change on that position. 3,1 cofactor, what's that going to be? Cross off row 3 and column 1, what's the 2 by 2 determinant? -15, right? And we don't change the sign on that one, so it's still -15. The 3,2 cofactor? Let's see, what's this little determinant gonna give me? 10. So what do we put over here? -10. Awesome. And finally, the last cofactor is going to be the determinant of the upper left corner, and what is that gonna give me? 2 minus -6, that would be 2 plus 6, which is 8, and I don't need to change the sign. Was that too fast? You get really good at this, trust me. Over the weekend, you practice this a lot, should go pretty smoothly. One thing I do want to mention, when we were doing cofactor expansion at the start of class today, you remember how we would go across a row or a column and we would multiply the entries of the matrix by the corresponding cofactors as we went across that row or column? That's a thing we don't want to do here. Literally what we're putting in this matrix is just the cofactors. I've seen students do things like this. They say, oh, they got an 8 here, but then they want to multiply it by 2 because they see the 2 is here. They're still in that mindset of, oh, I take the entries times the cofactors. And so they put 16 here instead of 8. You don't want to do that. You just leave these cofactors as is without multiplying. It's not like what we were doing earlier. Earlier, we were taking the cofactors and multiplying them by the entries of the matrix. Here, we're not multiplying them by anything. We're just calculating the cofactors and throwing them into that matrix just raw. Right? So you see the difference? This is the advantage I have. I've taught this class like 30 times. I know everything that goes wrong. I can hopefully try to head this off for you. I'm trying to think back to the first time I taught this class. I must not have had any clue what I was doing. I would not have known any of the challenges. This is actually, if you can come up with this matrix of cofactors, you're already 80% of the way to finding A inverse without ever doing an ERO, because there's not much more to it. Let me give you the next definition, but the hard work is just getting that matrix of cofactors. The next definition is the adjoint of A. And this is written ADJ of A is, this is an easy one. The adjoint of A is just the transpose of the matrix of cofactors. It's just the transpose of it. So all you have to do is transpose that, and then you're good to go. So for example, on the above example, I'm just gonna go right into it here. The adjoint of the matrix above is the transpose of what we just calculated here at the top of the board. So the first row becomes the first column. So 7, -4, -2 on the first column. The second row becomes the second column, which is just 6, 4, 2. And the third row becomes the third column, -15, -10, and 8. That's the adjoint of A. It's just the transpose of the matrix of cofactors. So you can write that down very, very easily once you have the matrix of cofactors. Okay, and so now I'm ready to tell you how to find A inverse using the adjoint. It's just a very simple thing. So this, I'll call this one actually a theorem. Let me call this the adjoint theorem, just to give it a better name. So the adjoint theorem. And here's what it says. It's just a formula for A inverse. It's just a formula for A inverse, and here it is. What you're going to do is you're going to take 1 over the determinant of A. Now, that can't be 0 on the bottom, because otherwise you don't have A inverse. So you're not dividing by 0 there. That's just a number. It's a scalar number that multiplies the adjoint of A. That's the whole thing right there. That deserves to be in a box. That is a formula you will want to learn. The adjoint of A. It's just simply, sorry, the inverse of A. It's simply the adjoint of A divided by the determinant of A. And to evaluate this right-hand side, you don't have to do any EROs. This is an alternative to the Gauss-Jordan method, where we now can find the inverse of a matrix just by taking the adjoint of A, which involves cofactors, transposing the cofactor matrix, and then dividing by the determinant in front. So let me, one more time, go back to the example from above. We would need to figure out the determinant of A over here. So that the determinant of A on our example above, I can get that one just using the arrow method. Right, so I can come over here and I can take this original matrix A and find the determinant with the arrow method. It's going to be 4. So remember how the arrow method works? You just recopy the first 2 columns here and then draw your arrows. So 4 plus 0 plus 0, right? Those are going to be zeros. And then minus the arrows that go the other way, which is again 0. And then minus -10. And then minus -12. So minus 0, minus -10, and minus -12. And if you work all of that out, it is 26. 26. That's it. So, if you believe my adjoint theorem, then I can tell you what A inverse is. So A inverse is 1 over 26 times the adjoint of A, which in our little example over here, we wrote down what that was. Let me move my computer. wrote down the adjoint of A, it was 7, 6, and -15. -4, 4, and -10, and -2, 2, and 8. If I did that right? Yeah. Of course, it is, I'll call this next thing I'm gonna write down optional. You can leave this as your final answer. But if anybody wanted to, it would be perfectly okay. This is totally optional to just put the fraction over 26 into the matrix. So you could certainly do this. And don't worry about reducing the fractions to lowest terms, all that kind of stuff that they harped on back when you were in your grade school math classes. I am going to be much nicer about stuff like that. And you want to leave it like this, you can. Okay, so this would be an answer. I do want you to ponder for a minute the thought of trying to come up with this answer the Gauss-Jordan way. So in other words, you know, you put your original matrix on the left side of a bar, and then on the right side, you'd put the identity matrix, and you would start doing EROs. Well, your EROs are going to lead you to these kinds of numbers into your process, right? Because this is the answer, right? And unlike this adjoint method, which sort of factors the fraction out in front of you in its very nature, the Gauss-Jordan method isn't going to be so friendly. The Gauss-Jordan method is going to have those fractions like crawling all over your calculations. I would take my chances with this, right, much sooner than I would the Gauss-Jordan method. Just looking at those fractions, I get a little bit queasy, right? So that's the point. Johnson?
Yeah, on the exam, are you gonna specify what method?
Oh, would I specify what method I wanted you to do something with? I probably wouldn't do that. I probably would let you do it however you wanted to do it. I will tell you actually what I like to do. Maybe I can give you, oh, I'm so excited about this stuff. I figure out which example I want to do. I don't want to do a full-blown example right now, but do you have that assignment number 8 in front of you that you were asking me about a moment ago? In your computer there in Canvas? Yeah, you were just asking me if you had to watch that video.
Oh.
Can you pull that up for me? Yes. All right, thanks. What I want to do is actually give an example of a 4x4, and I'm going to maybe take one from Tuesday's homework if we've got any of those numbers up. You got it here? Yeah, do you know which problems are assigned? That's what I'm asking about. You have which problems are assigned? So for 52, 59. Okay, actually, and that's in 3.3. Okay, thanks. I'm actually not going to do one of those right now. I'm actually not gonna do any of I'm not gonna solve this fully out. But this is just so you know, this is not off of the homework, but I wanted to show a 4x4. So here is the problem. And so this is getting back to what Johnson was asking. He's asking, will I specify what method you have to use? So here is an example. I'll just write down this matrix here. So the first row is 1, 0, 1, 0. And the second row is 2, -1, 1, 3. The third row is 0, 1, -1, 2. And the fourth row is -1, 1, 2, and 0. And then here's what I might ask. I might not ask you to find the full A inverse. Oh, well, the reason I might not do that is the matrix of cofactors, there's 16 of them. Every single one of them is a 3x3 determinant that you'd have to calculate. I don't think I'd want to make you do 16 3x3 determinants. That'd be pretty horrendous. Unless you guys have nothing to do next Thursday, we could spend all day on the exam doing this. But what I might ask is find the 2, 3 entry of A inverse. Suppose I asked you just that. So I'm not asking you to find the entire A inverse matrix. To find the entire A inverse matrix, you would have to find the entire 4x4 matrix of cofactors. That would be 16 cofactors. Each of those 16 cofactors would involve doing a 3x3. I mean, we had enough trouble just doing this one, which was 9 2x2s. Here we would have to do 16 3x3s. Exponentially more work. So instead of asking you to do that, I could ask this question, because this question only requires you to find one cofactor. So the answer here would be 1 over the determinant of A. Okay, so you have to find the determinant. It's a 4x4 determinant. It's very similar to the warm-up that we did at the start of class today. And then you would have to multiply that by, to find the 2, 3 entry. Which cofactor would you need to find? Say it again. 3, 2. That is absolutely right. We would have to multiply this by the 3, 2 cofactor. Why is that? Well, because if I want the 2, 3 entry of A inverse, I'm going to need the 2, 3 entry of the adjoint matrix. But the adjoint matrix is the transpose of the matrix of cofactors. So the 3, 2 cofactor, when I transpose it, it's going to go over to the 2, 3 position. The subscripts get swapped, right? The I and J, they swap when you transpose the matrix. Aij turns into Aji. So this is all you would have to calculate to solve that problem. I have a fully worked out example of this in my review session for the exam. I'm pretty sure there's one of these on the sample test as well. So definitely, I'm not going to do it now, but that's how you would do it. Okay, so I just wanted to show you if I, and the why it's related to Johnson's question is that he was asking, will I specify, do you have to use the Gauss-Jordan method or do you have to use the adjoint method? If I really want to force you into the adjoint method, I'm going to do this, because the adjoint method picks off a particular, you can pick off a particular entry of the matrix really easily, right? Whereas the Gauss-Jordan method, if I say find the 2, 3 inverse of A, the 2, 3 entry of A inverse, and it's a 4x4 matrix, and you try to do it with the Gauss-Jordan method, you still have to find the whole A inverse. You have to do the full-blown calculation, and there's no way to sort of pick off just one particular slot that you're interested in. Yeah. So anyway, I just thought I would mention that. Maybe on Tuesday next week, maybe I'll actually do a problem in full detail like that. Yeah, we'll see. But if not, there's definitely plenty of them in the resources, and it's a nice problem to do. Okie doke. So if you want, just, this is an odd numbered problem. You can try it on your own and check the answer. You only have to do 2 things: find the determinant of the whole matrix and find the 3, 2 cofactor, right? Cross that off, cross that off. I've got a 3x3. Don't forget to do the sign change on that odd entry, right? 3 plus 2 is odd, so there'll be a sign change on it. But yeah, this would be worth trying it out. I'm not gonna ask you to do it. I should have put this on the homework, but I didn't. Try on your own. Okay, really quick, I want to explain Cramer's rule, and then we will be done for today. So this is another application of determinants. And this is Cramer's rule for A times X equals B. This is if I want to solve a linear system. But this is only assuming that A is a square matrix. So if A is not a square matrix, this doesn't make any sense. And this needs to be invertible. So if the matrix is not invertible, then this method isn't going to get us anywhere either. But what this is this is a method for solving for X. Remember the unknown here is the X. Okay, so the goal is to solve for X. And let me just be really clear. We already know how to solve for X. We can write down A sharp. We can do Gaussian elimination to solve for the unknowns, right? That's perfectly fine. And even if A is invertible, we could actually just remember also, we also know that X is A inverse times B. But we also know that. So that we have already good ideas about how to solve for our unknowns. We can use Gaussian elimination. We can find the inverse of the matrix and multiply it by B. What I'm doing here is I'm going to give you just a different approach to it, an alternative approach, which is called Cramer's rule. And the way this works is, again, I'm going to give you a formula for each individual unknown. So let me just kind of lay out X here as a column of unknowns, X1, X2, and dot, dot, dot down to Xn. And here is the formula. And again, I didn't used to cover this in 250B. It was only after all my engineering students came back and said that their professors want them to know this that I started doing it. But I can tell you what the ith unknown is with a simple formula that does not involve doing any EROs. So the whole idea here, like with the adjoint method, there's no EROs here. There's also going to be no EROs here. There's just going to be determinants. And so what you do is you do a fraction. In the denominator, you have to put the determinant of A again. That's just like it was in the adjoint theorem. And again, if A is not invertible, then that won't make sense. If A is not invertible, then you do have to do Gaussian elimination, right? We're in a very special situation where it's invertible. There's a unique solution. Now, what goes on top of this fraction? Well, it's another determinant. And what determinant is it? It is a determinant that I am going to write as B sub I, where B sub I, which is also going to be the same size as A, it is n by n, is obtained by replacing the ith column of capital A with the B vector. The ith column of A gets replaced with the B vector. So you just take your matrix and you replace the ith column with whatever the given right-hand side column is. So if I want to know what X1 is, if I want to know the first unknown, I just take the first column of A and replace it with the B vector. Remember, B is a single column, so I can just put it into that first column. If I want to know what the second unknown is, I just take the B vector and replace it into the second column of A. And so on and so on. This is the Cramer's rule. I am not going to have time right now to do an example of this, but it's totally computational. It's pretty straightforward. On Tuesday, you have some homework for Tuesday on this. I'll let you try that out on your own. I do have a video that Marco noticed in Canvas of actually solving a full-blown example of it, but it's not anything interesting to, I mean, there's nothing new here. You guys know how to do determinants. That's all. So feel free to take a look at that over the weekend, and we'll talk more about it on Tuesday. That's all I got for now. Any questions as we wrap up the 4th week? All right. Thanks, guys, for being here. I will see you all again soon. Office hours are coming throughout the day today. Thanks, Adam.